Okay, so this is the introduction to the skeletal system. It's a relatively short lecture, but there'll be plenty more to come in the lab lectures. There's your objectives, functions of the skeletal system. Well, the skeletal system supports our body. It's what gives us shape and form, protects our organs because we have our body cavities are partially made up by the skeletal system. So the ribs protect the heart and lungs, cranium protects the brain. Production in the bones, we have red marrow that produces red blood cells, white blood cells, platelets. Storage, we store mineral salts within the bone. And in long bones, in the middle of them, we store lipids in the yellow marrow. And then movement. Our bones are places where muscles attach to allow us to move. Cells in the bones. First type of cell, osteocytes. Osteocytes are just the living bone cell. So the osteocyte is the actual bone cell. Okay, so these are bone cells. Remember from our tissue unit that bones or our connective tissue, and so you're going to have a living cell and then the non-living matrix around it. Osteoblasts are cells that build bone. So osteoblasts build bone. And that's what the B, a good way to remember this is. So these form the actual bone, create the bone. Okay, so these build bone. Okay, osteoblasts are stimulated by a hormone called calcitonin. So this hormone called calcitonin my pen is not cooperating. That's CI. Okay. And then osteoclast, these break down bone, are called cause bone resorption. And osteoclasts osteoclasts fall under or are affected by the parathyroid hormone. So, parathyroid hormone. That's one word, parathyroid hormone. Okay, so osteoclasts actually tear down or break down bone. Two kinds of bone tissue. We have compact bone. In compact bone, is densely packed together. So it's this bone here, that kind of bone tissue. And compact bone is very strong, gets a lot of longitudinal strength or strength along its length. And the other kind of tissue or bony tissue is this over here, and that's spongy bone. Spongy bone, as you've seen from your reading, is also called cancellous bone. So look in the book for that because my pen is not cooperating. It's all one word. Yeah, I'm even going to try. So it's cancellous bone. Is that spongy bone. And that gives more strength, angular strength. So you get more strength at angles. It also allows for a space in there, and within that space of that spongy bone, we find stuff like our red marrow. Bone classifications. We have long bones, which is what A is. Okay, so long bones are longer, generally longer than they are wide. And then up here at B, B is a irregular bone. So that's an irregular bone because it has an irregular shape. C is a flat bone, like the bones of the skull and the hips. And, sorry, I should have said B is a short bone. These are short bones. Okay, C is a flat bone. My pen is screwing me up, so I'm just going to put it away. And then D are the irregular bones. And then these round bones, this is like your kneecap or your patella. And this round bone is called a sesamoid bone. So I'm going to try doing it like this. Sesamoid. Okay, follow along in your textbook with this because technology is great when it works. Okay, this is the structure of a long bone and just the general structure of a long bone. And long bones have a shaft, which we call the diaphysis, and then these projections at the ends are called epiphyses, singular epiphysis. The long bone is surrounded by a piece of connective tissue called the periosteum. Okay. There's a cavity in the middle called the medullary cavity, and in these long bones, the medullary cavity is filled with a yellow marrow, and yellow marrow is where we store lipids. Okay. At the ends of the long bones, we have that spongy bone or that cancellous bone, and that's where we also find the red marrow. The medullary cavity is lined with another connective tissue called the endosteum. It's the endosteum. And the ends of the long bones where they articulate are called, those are covered with hyaline cartilage. So hyaline cartilage is the name of that tissue that covers that. Okay, this is looking at it in a little more detail, but microscopic structure of it. This structure of the long bone, we just took this little piece out right here so we could see the structure of the compact bone and the structure of the spongy bone. The compact bone is made up of these concentric circles of tissue, and that's what gives it its longitudinal strength. And those are called osteons. So you have 1, 2, 3, 4 osteons here. Each osteon has a central canal through which you have blood vessels and nerves that could be running through it. And then through those central canals are connected through a communicating canal called a perforating canal. So it allows you to have this lateral blood circulation. And then the spongy bone has all these little structures called trabeculae. And the trabeculae is what actually gives the strength to the spongy bone. When we take out an even smaller piece and look at that, we can see that these osteocytes, remember those living bone cells, those osteocytes are found in these little hollowed out areas called lacuna. Okay? And the lacuna are connected versus the canaliculi, singular canaliculus. Okay, and that's just how nutrients and waste are exchanged there. All right, bone development. Intermembranous ossification is when the bones originate in this sheet-like structure. I'm going to try the pen again. So the bones originate in sheet-like structures. And these are the broad, flat bones. Okay, broad, flat bones. To all the bones of the skull except for the mandible. So this is where all the intramembranous bones, or how they develop. And the endochondral ossification is when bones begin as that hyaline cartilage. So they're going to begin as the hyaline cartilage, which acts as a model. Okay, so the hyaline cartilage model. Okay. This is most of the bones of the skeleton. And we'll see, we're not gonna look in the intermembranous as much. Just know that it's for the broad, flat bones, and that the bones develop in the sheet-like fashion. Okay, here's the endochondral ossification. And with the endochondral ossification, you get, you start off with this hyaline model. So this is all made of hyaline cartilage. And the periosteum is what develops first. Okay, and what you get from that periosteum, or through the development of that periosteum, is you start to get calcified cartilage. So the cartilage in here becomes highly calcified. And this is the primary ossification center. So we're going to start digging out a medullary cavity out of this bone. So which cells would be involved with digging out a medullary cavity? That would be osteoclasts. And the osteoblasts are actually building the bone. After that, you get the secondary ossification centers. And for someone who's still growing, we keep these epiphyseal plates. And these are the growth plates that you hear so often about. And these growth plates or epiphyseal plates, you should always label them epiphyseal plates, don't label them growth plates, is how the bones grow longer. Okay, eventually the epiphyseal plates turn into epiphyseal discs as they become calcified and we no longer grow. Okay. So now we're going to look at how growth at the epiphyseal plate happens. So just to go over this again, start off with a hyaline cartilage model. You get the primary ossification center, and you develop secondary ossification centers. Epiphyseal plates stay for as long as we're growing, and when we're done growing, they become ossified. Okay, so this is growth at the epiphyseal plates. And we're looking at one of the distal ones. So we've got these resting cells which aren't really doing much other than waiting to start dividing. And once they undergo this rapid cycles of mitosis, these cells will divide quickly and away from the epiphysis. As they grow, they become mature and then they calcify. And when they calcify, they die. And so these are all chondrocytes that are dying. And eventually they're going to be replaced by osteocytes because the chondrocytes died off. So start with resting cells, rapidly dividing cells. These chondrocytes are dying, becoming calcified, and then here they're being replaced by osteocytes. Okay, and this is the same thing, just a different way of looking at it. We've got those resting cells, these rapidly dividing cells, the ones that are maturing and dying and becoming calcified. This diagram just shows how bones act, and really it's just here to give you some reference to why we even look at this. It talks about the lever systems. So anytime you look at a lever, you're going to have a fulcrum, so the point which the rigid bar rotates around, some force, so this would be a muscular force, and then some resistance. And so for that first class, you have the fulcrum in the middle, the resistance on one side, or the load, and the force on the other. For a second class, you have the fulcrum at one end, the load in the middle, and then the force on the other end. And then for the third class, you have fulcrum on one side, force in the middle, and the resistance at the other end. So this just gives you some background as to why we even talk about this stuff. And this gives you that example. So here we have fulcrum in the middle, force on one side, and load on the other side. Okay, and this is just how bones work with the muscular system to cause movement. All right, these bone breaks. Bone breaks happen because of a variety of reasons. It's not always just bones getting older and weakening. Sometimes we just hit them. So a green stick fracture is an incomplete break. Quite often the green stick fractures happen across an epiphyseal plate. Okay, so the bone doesn't break all the way through. A fissured fracture is a break that's in a longitudinal manner rather than transverse. So when these happen, you get a crack along the longitudinal and it won't break all the way through. Comminuted fracture is when you get a bunch of pieces. So maybe a bullet passing through the bone or a severe break that breaks into a bunch of pieces. Transverse fractures are at a right angle to the bone. Oblique fractures occur at an angle that's not a right angle, so and it's not fissured. So these happen at an angle, And a spiral fracture happens because of twisting. And in the winter, we see a lot of spiral fractures for people who are skiing because either in their tibia, when they're skiing down and their legs twist and it causes a spiral fracture there, or when they fall and they land with their arms outstretched, you get a spiral fracture that way. Um, and then all of these, but more so the complete break ones, can be further classified as either open, which used to be called compound, or closed. So you can have an open fracture or a closed fracture. Open means the bone fragments are exposed to the outside of the body. Closed means that there is no fracture on the outside of the body. And open fractures are dangerous because of infection. Bone fractures and healing. This goes into a lot less detail than what's in the book, so just look at this. It's a lot like what happens with the skin. So you're going to get a hematoma or blood clot forming in here, and that is going to be replaced with cartilage. The cartilage will become calcified and then replaced with bone cells, and then the bone will change. Okay, so nothing major here, just blood clot, calcification, or cartilage, calcification, and then bone remodeling. Factors affecting bone growth and development. You can read those for yourselves, but some of the big ones are, well, vitamin D. With rickets, vitamin D is needed to get calcium for calcium absorption. And vitamin D is converted in our skin with sunlight. So in the winter, 100 years ago or 200 years ago even, people would get rickets a lot, especially in New England, because they would not get enough sunlight, and that lack of sunlight would mean a lack of vitamin D, and their bones would become kind of rubbery. And then they would twist into weird forms, and then they would harden that way in the spring when they actually got more sun and more vitamin D for bone, for calcium absorption. Insufficient growth hormone, you get dwarfism, excess gigantism. So sex hormones, estrogen and progesterone, promote those bone formation. We'll talk more about that in the endocrine system. Lifespan changes. After about age 30, we start to shrink. Calcium levels fall. Because of that, our bones become brittle. Osteoclasts. We have more osteoclasts than osteoblasts. More fractures will happen at the spongy bone. And menopausal women become even more subjected to bone loss than others because loss of those estrogen and progesterone. And then hip fractures are common, and vertebral compression fractures occur because our vertebrae become less plastic. Okay, and this is someone's bones, a premenopausal woman in her 30s, and then the same bone tissue 15 years later. So you can see how much spongy bone you can lose. Okay, that's it for the introduction.